right. April. My screen. Here we go. Do you see my screen? Okay. All right. So yeah, April was a really great month, I would say. Lots of things got done. So it was a lot of fun to put this together. But first of all, let's start again with the shout outs to the community. So we had actually a lot of first-time posts, a lot of new people on the Discourse forum who posted for the first time. So just to highlight a couple of interesting ones. So for instance, Bolton posted about using Monty for industrial SCADA sensor layouts and how that Monty might map onto that and how movement could be interpreted in this application. And then Colin introduced himself in the introductions, and he has a pretty interesting background with knowledge in GPUs, and is actually really interested in contributing to the project and like looking into how he could help maybe implementing an alternative simulator or GPU acceleration for Monty, which is really cool. So hopefully that turns out to happen. That would be great. And then, yeah, lots of people welcomed him. And generally, this introductions group is nice because then people can reply, like, hey, I'm also in San Francisco. If you ever want to meet and chat about Thousand Brains theory. And yeah, a lot of you guys also welcomed him. So that's great. And then Artem posted here about some potential improvements on the code base and how you would make those improvements. And he actually opened a PR about that later on. Dan wrote some questions about Monty and space representations and some assumptions about hardware that analyze it. Ben introduced himself also in the introductions channel. Some interesting background. Ski, I'm not sure the real name of this person, but posted some longer threads about one about evaluating on the OmniGod dataset, and then a further deep dive into like speeding up Monty, and actually seemed to have looked into implementing Monty on other datasets that we hadn't implemented yet. So that's cool. And then some questions from Arun, who posted for the first time about Thousand project and how it relates to HTM. Don posted something end of last week on the behavior, object behavior disclosure document. And then there were generally some other interesting questions. I'll just highlight this one from AK90 that I liked. Because because I wrote a lot on it, but it was an interesting conversation about abstract concepts in Monty and how language could be represented in Monty. So I thought that was a really nice thread. And then, yeah, several people working with Monty. So like I mentioned, SKJ, looking at the OmniGod dataset, and then actually seemed to have implemented Monty on the MNIST dataset as well, and kind of looking at the runtimes and how that could be sped up. And then just generally, looks like 150 people have forked our repository and about twice as many have started. So it looks like people are looking into the code and potentially using it. So hopefully we'll see some of that showcased in the future. Sorry, I might be coughing a bit today. And then here's the PR that I mentioned from Artem about adding some typing to the code. And then we created a MISC category in our Discourse channel where Humble Traveler posted a book he's writing called The Idyllic Mind. And yeah, kind of TBP inspired science fantasy project, and shared like a Google Doc. I didn't have a chance to read it all yet, but I saw that some other people left some comments on it, which is kind of cool to see. And then yeah, he also shared these kind of images from it if you want to see some visuals. And then also people sharing the Thousand Brains project. So Matt Roberts sharing that he's excited to have Tristan speak at the Agile Austin conference, and yeah, liking Jeff's book. Leonel Bischoff shared or commented on our work and how it is really nicely aligned with some other related papers, like this recent paper from Sutton and Silver about how now we're entering the era of experience where AI learns again by interacting, even though that talks a bit more about agentic LLMs. That's a nice mention, and then also here another nice post by Sanath about, yeah, that people should check out Numenta and the Thousand Brains project and how we've been working on bridging the gap between AI and current understanding of how the brain works. So yeah, thanks for sharing the project, and thanks for everyone in the community interacting on the forum and asking questions and looking into the code and starting to contribute. So now to our monthly review. So this month, I would say was really productive, and maybe that's indicated by this rather empty calendar, so not a lot of holidays and stuff going on. Next month will look quite different. But yeah, I'll start again with discourse just because we were just talking about that. So a lot of people from our team interacted on discourse really nicely. Like Hoj posted a bunch of replies. Also Will and Tristan, Niels, Rami, Scott. Really lots of in-depth and nice replies. So just some examples here from Hoj replying to several people about like some people shared research papers on the discourse channel that she replied to, how that relates to Monty, and just kind of asked some clarifying questions on other people's questions. And then Rami also had some longer in-depth posts about questions that were asked about his internship work on the SDRs for object similarity encodings. Will reply to a couple of questions and then also did some nice moderating tasks like moving topics into their own thread and creating the MISC category and allowing people to upload PDFs now. And then, yeah, Tristan also had some interactions with Colin. I didn't say this in like the previous section, but he also actually met with him over a video call to talk more about getting involved and what potential things to work on. And then also for Artem, who asked about how to contribute to the code, Tristan made like a really nice overview of like when should you write an RFC or just make a pull request and how we kind of think of that process. And then, yeah, also Scott and Niels give some nice in-depth replies to people's questions. And then I also had some interactions with several people. The guy I showed earlier asking about using Monty for SCADA data, which unfortunately I don't think Monty can be used for yet. And then Ski about the object recognition in Monty, making it faster and using it on Omniglot, and then this longer thread about Monty on abstract concepts and language and how we think about this.
So I start off with a very simple experiment, so please pay attention to the screen. So what did you notice? It's a bigger handle. Okay. Huh? A bigger handle.
Oh, I didn't know I was supposed to notice that.
I just moved to the bottom right. You moved to the bottom right, correct. Just repeat it. It's identical. Is it? Yeah, it looks identical and it obviously moved. But these are the two images. So you see the quite a difference in size. And I guess if a wizard would come into at night, go to our cupboard and suddenly or magically reduce the sizes of all cups by half an inch, you wouldn't even notice the next day.
I think I would. That I would notice because you have this sort of physical memory of what your hands feel like, right? This is not because you see objects at different scales all the time. So neither one of these is correct scale, right? One is just one's bigger than the other, and so now it's more of this sort of change blindness.
Yeah, that's kind of change blindness.
Not quite.
But the point I want to make here is, on one hand, it's very obvious to compare the two, and we can clearly represent the dimensions of those in comparing the two. On the other hand, we can recognize it independent of the specific size. And the way it appears is a different way it appears in my hand. We can recognize it the same way. So how does it come about? So that's what I want to address. Those two different things. And I already shared this last time. We have, in terms of recognizing the cup, we have quite some flexibility to recognize the distortion. And it's sheared and tilted in a certain way. But there's also limits to the distortion. The last one, what is the upper ring on the cup looks more like a face. Looks more like a cartoon character.
I don't know what's a fingernail.
Oh, it's a fingernail.
You spend too much time thinking about fingers. Depends what you focus on.
And
need a manicure.
yeah, so suddenly it looks so the recognition, even the recognition is different. The point I want to make here, our recognition is flexible to some extent, but there's limits. You have sort of taken into the relative
Don't you
locations.
think this is different than the scale component, right? Don't you think that? I mean, the scale difference is really quite qualitatively different than this.
Yeah.
Okay. They're not. I wouldn't call the scale one distortion. I would just call the scale one whatever scale it is. Right?
And so we seem to have two kinds of capabilities. On one hand, we recognize the object's invariance to position, pose, scale, and deformation. On the other hand, we recognize the specific position, pose, scale, and deformation.
I guess I'm going to object to the scale thing here on the second one again, because it's not clear to me we actually do recognize scale. Clearly, I can know where it is relative to my body. I know the pose relative to my body. I can know if it's deformed. But the example you gave of the two cup scale, I didn't see them as different. That's just because I think scale is like an uber factor that's applied on that, right? Especially when it comes to vision, because we see things at different angles, at different distances. It's not like I recognize the scale. It's like I recognize independent of the scale. So I think with touch, I would definitely say, yes, I recognize the object scale. Like it gave me a small version of this cup, I would feel it, I would know it. But with the vision, I'm challenging. I don't think I do recognize it. I think scale is fun.
I feel like there's two different uses of scale here. One is the object itself smaller or larger, and the second is the image on our retina smaller or larger. Those are two very different things.
Yeah,
because
right.
if we're doing completely in 3D, the size on our retina doesn't make a difference. We're sort of invariant to it, but if it's physically smaller or physically larger, we do know. Like a tiny version of this, I would immediately know it's smaller, but if it was further away, I would still think it's the same object.
If there was context, if I see this cup in the context of other things around it, I can tell if it's smaller or larger. But if you just show me the cup, independent of context,
I agree. It depends on the context, and I'll get to it.
But
it depends what you mean by scale here. It's two different meanings.
In a sense that we recognize it in the context. Right? Like this cup compared to the same kind of cup on a smaller scale stage.
Yeah, a smaller cup.
Yeah.
But again, I don't think I can tell the difference between those two if I don't have context.
Yeah.
Right?
In the context.
Right? Because without context, I don't know if it's a faraway cup or a close cup or a cup that's smaller or bigger. It's meaningless.
Right.
Like we've shown pictures of the coffee cup on the screen 1,000 times. It's never the size of a coffee cup. you know, we didn't look at those two pictures and go, wow, that's really big, you know.
Yeah, I think context is important.
Well, again, I just want to say that I don't think scale. I think scale is a different problem than pose, position, and deformation.
Yeah, that's it. So 2 weeks ago, I presented you the exercise with trying to reproduce 3D objects from memory without looking at it. And here I tried something similar, but instead of just reproducing the whole object, I placed a smaller object on the other object. And I found it seems fairly easy to reproduce the position on the object. So you seem to have a good sense of the position of one object on the other, on another. And then even though I didn't get the whole dimensions right with the keyboard, the perspective is again wrong. And the box with the arc on the bottom is a bit distorted. But the location of the object is fairly accurate. So that's one observation. So with this comes my proposal. So there's two processing pathways. And on one hand, we represent the object in a reference frame of another object, and it's a supporting object. For example, the cup on a book, on a table. We have a representation within the coordinate system of the supporting structure. Where's the cup located? Where are features on the cup? For example, shapes, where are they located in the reference frame of the supporting structure? That's one thing. And the second path would be, we have this invariant representation that's like in a local reference frame of the object itself this time, but where we don't take exact locations into account. It's more like I have this curvature feature here and sort of somewhere relative to each other, another feature, and it represented in a way that is invariant to the rotation.
But why do you say those are different? I'm confused by that. It seems to me, you know, the logo on the cup is just another example of an object on object.
Yes.
And so cup in the book, I mean, why do you say these are fundamentally different? It seemed to me
it's a very similar process.
but what's different about it?
But there's essentially two differences. One is we use a different reference frame for the first one, that is from the supporting.
But what is different about the first one? Why are you making that argument? Why do you say there are two different? Like I look at this and say, okay, I can take any object and show its position relative to another object. Mm-hmm. In some cases, that's a permanent thing, like the logo on the cup. Some cases you might think it's a temporary thing, like the cup on the book. But if that's the way my book came, if a cup on the surface, then I'd say that's the object. So I'm not sure I'm understanding the fundamental difference between these two. Don't say in terms of what the reference frame is, like what structurally what's different about it, you know?
Yeah, apart from the reference frame is the position, right? First, we decode the position of the object in that reference frame.
But isn't that what the logo is doing on the cup too?
But that's the same. The logo on the cup is the same case as the path one.
Okay, so then what is different about path?
I should have an example here.
What is different? Is path two sort of the morphology argument I was making? What is path two?
Path two is the argument related to what we discussed before about the displacements and the displacements relative to the local pose. And encoded in a way that's completely invariant, almost completely invariant to the rotation.
But couldn't you make the same argument on the left? I could just rotate the whole thing. And I mean, to me, I've felt there's two things that I've been struggling with. One is you've got things which you can't say object A and object B, which is like the circle or the curvature or the morphology of an object, where there's no points where I can say there's a reference frame relative to a reference frame. And then there's this idea that maybe there's this, you know, maybe there are other times when you can say there's specifically like this thing is located at this location to that thing. So I've been struggling with this morphology versus features displacements, but I'm trying to unite them. Here, I'm not sure if you're saying like the same thing. If it's like you're talking about local shapes, that's like the morphology argument. I just want to make sure if that's the same as what the morphology argument is thinking.
Well, everything is about morphology. The local descriptors are like local, let's say, local shape descriptors. But here it's represented in a way this is not a specific coordinate. Right? This is just so this feature is located relative to this feature, and just to the, let's say, to the northwest of it, northeast of it.
But isn't that similar to the cup on the book?
No, in this case, we would have a precise location representation. So there's a representation in this coordinate system, and this XY coordinate, or maybe this XYZ coordinate, there's this part of the hand. We directly represent in this coordinate system where is the handle
in the book's coordinate system.
in the book's coordinate system. Whereas in this case,
yeah, I guess I don't know. I guess I'm going to keep pushing back. The way I think about how I recognize this cup on the book, I don't recognize the features of the cup relative to the features of the book. I can say, here's this cup, I already know it. Here's a book, I already know it. And very rapidly, I can associate the book and the cup together. And I don't do that by associating all the features of the cup relative to the book. I mean, that's the whole point of the compositional object, is that I don't need to study all the components of the cup relative to the book's reference frame. At least I don't have to do that to learn it. I can just do it in an instant. I can just, in one sense, I can say, oh, there's the cup relative to the book, done. And maybe I can calculate those positions, as you show, like where's the handle to the book. But I don't think I memorize that. I don't think I would even have the opportunity to do that.
though, yeah, I surely wouldn't do it in a way that's very detailed, right? But it will be very sparse representation.
But why would I even do it at all? I mean, it just seems like I don't even have to see all the parts of the cup. It's somehow I'm able to say, if the cup is relative to the book, then that's it. It's very rapid. I don't have to look at the different parts and calculate the differences between them. Anyway, if you store it this way, then it seems like you just have this compounding problem of then you get this explosion of things you have to memorize. The relative items relative to other items at all points can get very complicated. I mean, it seems like we do this very rapidly. We just say, okay, there's this existing object, like the Dementa logo. I don't have to specify all the components, memorize all the components of the logo relative to the reference name of the cup. It just seems I'm able to do the whole thing at once. I'm saying take the Dementa logo and apply it to the cup. And
well, I see the advantage this way. So for example, this representation allows us to quickly recognize the object independent of the pose. And this would allow us to represent what is actually the pose of this thing in the world. That, for example, the handle, and I just need a few key features, right? Maybe the bottom of the cup is at this location, and this piece of the handle is at this location. And through this pathway, I recognized, oh, this is a cup. And this representation would tell us, okay, there's something like a handle feature here, and there's something like a bottom of the cup.
This is still confusing me. I think we just have different languages for these things. You know, on the one hand, we talked about the what and where pathways, right? And the what where pathway basically shows where things are relative to a body-centric reference frame. Right. But you don't know what it is, right? So it just says there are things out there at this position. Right. And then you've got the what pathway. It says, oh, and here's this thing called the cup, but you actually don't know where it is anymore, right? It's like it's just in its own reference frame. Right. So that's kind of what you're talking about here.
Yeah, that's kind of.
But I always view those as basically the same mechanism. You're just using different reference frames. Like one is the reference frame of the cup, and one's the reference frame of your body. But when you said the book, well, that puts it back in the what pathway. It's like, okay, I have a book and a cup, and they're relative to each other. Well, I could have that in any position, any pose, and I still see the book relative to the book, cup relative to the book. So I feel like we're mixing ideas here. And we're talking also between reference frames and displacements, right? I think you're saying on the left you have a reference frame, on the right, like a XYZ reference frame, but on the right you have a displacements, right? But you also show a reference frame. So I'm confused by that also.
Okay, maybe let's have a look at some more examples. So in this way, you could also think about the deformation. Recognizing the deformation would have been in this reference frame would have been different coordinates. This way we could represent the deformation in that way. And this would be further out here, where it's stretched. So it would have a different location as opposed to just the object on its own.
So but couldn't you represent the deformed cup on its own? Why are you tying it to the book? I'm confused by that. Right?
Because we had struggled to find a representation for the object just on its own.
But that was your path too, right?
Yeah, but with the path too, we could do it in a way that it's completely invariant to the deformation. There's no optimization process involved. What would be the appropriate deformation, rotation, and transformation to get to recognize this cup in this particular configuration?
So okay. We had the problem of recognizing the deformed cup, right? Problem, like we can do that. We can see the same structure in different shapes and different sizes and different deformations. That seems to me basically an object recognition problem, representation problem, which to me puts it in path two. It's like, okay, it doesn't matter the orientation, it doesn't matter its relative look, it's just a cup can be different shapes. So I'm confused why. Well, it seems like that's a fundamental problem of just cups, not cups and bowls. That makes sense? Or I just think I'm missing something. You're trying to get across.
It's yeah. I think that there's two separate questions. One thing, how do I recognize the cup in a completely invariant way to those deformations? And the other thing is, how would these deformations be directly represented in a straightforward way? It appears to be within the context of another structure, because I can imagine it's.
But why? Can I recognize this cup independent of another structure?
I can recognize.
I mean, recognize it as a different shape, different form, different. You know, this. I can tell this is a shorter cup. Can I do that independent of another?
In principle, yes, but then you might have an explosion of the number of possibilities.
Well, it seems like it's still been put the number of possibilities. Obviously, we don't. It seems like I can even do it. I can recognize cups of different shapes, independent of their context, and I don't have, my brain does it, so it must be a solution, right? To me, it feels like I've got to solve that problem, the deformation problem, one way or the other, independent of its context. And again, I think that the size scale change of the skies you started with was not a good, that was a different example. That's why I was trying to separate that out. But here, I would see this, if you didn't show me the book, I'd still see it as a deformed cup. I don't need the book to show me that. Or not deformed, it's just.
But it's hard to present something without any context, and the context could be the
It's
TV
self-context. It's just self-context. It's a difference between an oval and a circle, right? It's a self-context. I don't need a context to know that a circle is different than an oval. I can just see it. There's a representation of that shape, just like I can say that I have a representation of the cup. That's independent of context. That says it's shorter, taller, whatever. I mean, context can help. Like when you're talking about the absolute size of something, the context would provide that information, right? So if I see the cup and it looks bigger on my retina or smaller on my retina, well, how do I know it's a bigger cup or a smaller cup? I have to look at the context.
Also have a lot of information on the shadows and the lights and stuff. It's not just.
Yeah, but right. But still, I think it seems to me this problem can be solved independent of this context at all. I mean, it has to be solved. I guess my argument, Heiko, is that I see this problem independent whether there's any context. If you showed me a short cup and a tall cup, I see it, and that's all there is. I know one's short and one's tall. Well, I know their relative sizes, if they're internally consistent sizes, or morphology, it's independent of any other context.
Yeah. Or maybe if there's no other context out there, it could be still the body reference. imagine.
It's, why can't it be the cups reference frame? I just don't get it. I don't get why the cup reference frame is insufficient for this. Cup reference frame, it's self-consistent. I don't need anything else to tell me that, you know, that this cup is wider than tall and the other one is taller than wide. It's this obvious. It's self-consistent reference frame.
Well, and
you try to draw analogies with the what and where pathways, and
yeah, that's
think of
one thing I was
why we
thinking
maybe-
about, what and where. On the other hand, when looking at the literature, it seems quite messy. So the behavioral experiments.
yeah, I mean, the thing that's clear is like where is stuff that's relative to the body and how the body might interact with the object, as opposed to kind of the what pathway, which is just about the object identity and its own essence, if you will.
I think that's pretty clear. I mean, every neuroscience thing is messy. There's no study it's not messy. But I think that's pretty clear. As I said, it's, you know, there's. I mean, the people who push around the edges saying, "Well, I found some blah blah cells that respond this way or that way," but you know, generally, it seems to be pretty well.
And I think what it shows is there is some separate processing of the object identity.
Yeah, well, I think it's very easily explained in some way. I'm not sure this is right or not, but if you think about a reference frame relative to the body, then the where pathway basically says these are things relative. You know, this is where things are relative to the body, and I can't. If a reference frame relative to the body, I can't define the object. Right, the object is not defined in a reference. It has to. The body has to be defined. I mean, can't find the object that has to have its own reference frame. So the what pathway is like, oh, I'm going to use the same mechanisms, but now I'm using a reference frame that's attached to that object. And so I'll see the shape of the object, but I don't know what it is. And here I see where something is, but I don't know what it is. That's very, very simple and copacetic with the mechanisms and with the observations of what pathways.
But I think I see the advantage of having also a reference frame with getting other objects, let's say supportive objects. We can build up the whole world in this hierarchical world.
Yeah, but that's just a compositional object, right? Or a hierarchical object.
Yeah,
I mean, that's the coffee cup itself is that way, right? The coffee cup has a logo, and the logo has letters and word and letters, and so that you can build up that structured compositional model in the what pathway. I suppose I can do it in the where pathway perhaps, but I don't think I need to have a body or world-centric reference frame to learn the structure of the object. Again, to me, the book is just it's just a composite object. If the book is just another thing, I don't see how it's different than the logo on the cup versus the book in the cup. Because the book could be tilted and change its direction, right? You could do all that as well.
But I have the feeling we can represent, let's say, object A very well in the reference frame of object B. And then, for example, the key on the keyboard is a very specific location relative to the computer. And if I change my own perspective, it sort of keeps in this.
How's it different than the logo on the cup? I don't get it.
It's the same.
Okay, so then I'm missing what you've introduced here. I'm just not following your argument.
It's the thing with the logo is it's represented within this curved coordinate system on the cup.
Yeah.
So the cup is now the supporting structure.
Yeah.
And then the logo is represented in this reference frame, and the locations of each letter is represented in this reference frame of the cup.
Okay.
It's not the reference frame of the logo, it's the reference frame of the cup.
Right. So, but that seems exactly what you're saying with cup to the book.
Yeah.
So then I don't see them as two separate mechanisms.
Yeah, this is part of the part, like I said, part one. This is the same.
Okay.
What is separate is the ability to recognize like a specific shape, maybe one of the letters, independent of this deformation. And in this case, they wouldn't have a specific location-based coordinate representation.
Right. So the way I've been doing this is there's two possible ways of representing things. You've got a coordinate reference frame, and then you've got displacements, and these are two possible representational schemes.
Right.
The coordinate reference frame, it's very difficult to handle certain types of deformations and so on, right? You know, it's like, but and it's very difficult actually to infer what the object is in the coordinate reference, because you don't know where you are. How do you even assign it to the right reference frame? It's like, who knows? But when you deal with displacements, it automatically handles those things. Displacement says, oh, it doesn't matter where this thing is. I'm just looking at the displacement features. And then we talk about how the displacements themselves could be modified and morphed as long as the relative positions of features are preserved, but the distances between them could be stretched, and you still see it as a deformed object. So to me, those are the two worlds that are possible: reference frames and displacements.
Right.
And if that's what you're talking about, I agree. There's these two possible representation schemes, but I don't know if they're both being. It seems like they're both being used in the representation of an object.
Yes.
And it's not like there's one pathway and another pathway. It's like object representation has both these mechanisms,
Right.
and they serve different purposes.
Mm-hmm.
So to me, it's not like path one and path two. It's like, oh, how do I represent an object? I have to come up with some mix of displacements and reference frames to do this.
Yeah, I agree. It might not be path one and path two, and it could be very well everything is in one column, and it has. But I essentially talk about these two types of representations. One is the specific location-based representation, and then it needs some supporting structure like the cup and the logo. On the other hand, I have this displacement type of representation, which is invariant to a certain amount of deformations.
Well, it's certainly invariant to pose. You can change your pose of things, right?
Right.
You know.
And so I would, so this is, oh, sorry. So this was, I was thinking, according to maybe path two is not the right term, but it's according to the other way to represent it. And because we have this ability to recognize things, I think just based on rough relative displacement from each other. For example, if I hold this cup on a corner here, and I now blindly would feel the rim over there, and it will still feel like the cup. And so it's sort of like it's this relative displacement with some leeway, sort of like coarse-grained representation. And it's also like would be relative to this part.
Well, this is just the displacement idea, right? Yes.
Right. And this local shape here is an orientation. This would be just relative to that.
Yeah.
So it doesn't matter how the whole object is oriented. The course of the whole object.
Right.
It's strictly invariant.
This is a displacement representation.
Yeah, exactly. And so regarding the encoding, so what I call path one, we didn't use the location as a context, and for each location, we would expect a local shape.
This is what we did in the columns paper.
Yeah, it's essentially the columns paper.
Yeah.
But maybe the only difference is I call it as like some supporting structure. Right? It would be like the book or the cup itself or the logo. And versus the other one is uses as context the displacement, and I expected a certain displacement and the certain local shape.
One of the you say here, what was it? You said, what's it? I thought I said, what is it for? One of the possibilities is that Marcus had proposed was that grid cells, which are what we think of when we think about reference frames, right? That we know that they do path integration. They know that they allow you to know where you are when you move, and they're also more ideally suited for determining basically the distance between how you might move, as you say here, like playing actions. And so there's this idea the grid cells might just play a supplementary role. They're not really in the definition of the object itself. The object is defined by its displacements, which is kind of a more copacetic idea. It makes sense. But then you might have this reference frame because you actually have to move relative to the object, and you have to calculate movements, and you have, so it's more like you can link to that and use that to define how to move, but as opposed to actually being the integral part of the representation of the object itself. So we, in the columns and columns plus paper, we say, oh, the object is defined by these reference frames and features relative to the reference frame. Maybe that's completely wrong, because it doesn't work really very well, but maybe it's all about displacements, and the reference frame is there as a supplemental role that you need when you want to move relative to the object. As your finger moves, where will it be relative to the object? So that's, I was just reacting, what is this encoding for? Right. And I guess it's under possible planning actions, but that is the hypothesis that that I'm kind of working with right at the moment, because it seems like if we can define the structure of an object completely independently of these reference frames, it is all about displacements. That would be probably how it's going to be done, right? Because every time I think about using reference frames for defining the structure of an object, it doesn't work really. It doesn't work well.
Yeah, for example, in this case, if I represent like this shape and this, or let's say the keyboard shape and the reference frame of this computer, then I could use this to guide my hand actions.
But you have to know when your hand is moving, how far did it move relative to the object? And we know grid cells do that, right? So that's a suggestion. Grid cells seems to be the way that movement is converted into displacements in some sense.
All right. So I think there's only one last. So as a last piece here. So I'm sorry that is kind of technical.
Yeah.
So I've been discussing with Vivian other invariant representations. So Vivian already showed that she can have a post invariant, scale invariant representation, and the object can be recognized independent of the scale and the post. Then we were discussing other kind of transformations, and for example, shear, or generally you could say an affine transformation.
What's a shear transformation?
Shear is, for example, this box is it's not flexible.
Not twisted,
not twisted, but imagine the top part.
Okay, yeah, okay. All right. That's a very odd. That's not a normal. That's not a very normal type of. I know what you're going to show me.
It would be like the
left one there. I mean, it's interesting. You show me that, and I would say that's fundamentally not a regular coffee cup. No, I'm serious. I think that distinguishes things, right? There are, I mean, you can change the size and the relative dimensions, and but I can see that as clearly a cup that's been, if you want to call it a shear transformation. I can see that. It's not like I said, oh, that's a new type of coffee cup. I'll say, oh, that's unless I guess if I saw a lot of those. That's sort of an odd one, I guess.
I mean, you also see the rotation and the scale. Just because you see it doesn't mean you can't recognize it as the same object anymore.
I didn't thought, the words made sense, but I don't know what the point you were making. Really.
So like also when the cup is rotated, you see that it was rotated, or when it's been scaled, you can see that it was scaled. Under all the transformations, you still recognize it as a cup, but you're also able to determine that there was a transformation applied to it.
Well, maybe. I mean, when I see the rotated coffee cup, I don't say to myself, in fact, this is what the argument I was making last week. I don't say to myself, oh, that's the coffee cup rotated. Remember, I was making the argument about sort of all views of the coffee cup might be laid out in a sheet. I don't say, oh, here's the coffee cup, and now, oh, I'm looking at I see it now rotated. It just looks, if you say, what is that? I don't say, that's my rotated coffee cup. I don't, you show me this, I don't say, oh, that's my coffee cup looking down from above. I see that as a coffee cup, but it's not like I have to do a transform to get it into some canonical view in my head.
Right.
And that's where I was coming from with that.
Exactly. That's exactly where I was coming from.
Well, the shear one is not like that. I look at the shear one as like, no, that's wrong. Right? My coffee cup doesn't look like that. So I say there's a fundamental difference between, distortion of changing the morphology of the cup, distorting in some way. The shear distortion might be just the same as making it squishy or short or something like that. But I see that as different. I don't see that's my coffee cup. I immediately know it's not my coffee cup. But when I look at the different views of this coffee cup, I don't see it as a different object. I don't see it as my object rotated under some deformation. Rotation does not seem like a deformation.
But Jeff, what if it's upside down? Then you would see it as.
If I see my coffee cup upside down, well, I'm like, it's in the closet, it's upside down. I don't have a problem with that. Right? If I see that, that is normal. I mean, first of all, even though I would say it's the same cup. It's the relative displacements haven't changed at all. So it's the same cup. As soon as you start changing the displacements, well, then it's like a circle becomes an oval. Like this cup becomes something else, but still related. All rotations seem to me, they're not like I got my object and I see it under some deformation. It's that's the beauty of the idea I was presenting last week, is that it gets rid of that idea. There's no concept that there's a left and right to this coffee cup. And it's just that somehow I see them all as the same. Where if you do some real deformation, then I don't see that. Then I say, oh no, that's shorter, fatter, different color. I don't know. I see it's different. But any of these pose changes do not strike me as it's a different cup. In fact, I'd say it's the same cup, even upside down.
Right.
Same cup.
But if this relates to the problem, what deformation do we actually consider to be the same?
Well, that's why
when does something become a different object?
Well, we were talking, there's two things. One is, when is something, a specific instance become a different object? So this particular coffee cup, when do I see it's different? And there's another question that's like, what's a normal coffee cup generally? Right. So that's an interesting question. I would argue under the deformation category, we just have to see what we observe in the world. If I never saw a tall, if I never saw a cup that had a rounded bottom, like a teacup, or like, and every cup I ever saw in my life was straight sided like this. And the first time you showed me a rounded bottom one, I said, well, that's not normal. That's odd. But since I've seen them all, I said, no, that's the difference. They're both coffee cups, straight sided and curved cup sided. So obviously it's experience based, but how we learn models of things.
Right. Yeah, then it gets messy. Right? How do we categorize it and stuff?
Yeah.
Category.
Yeah.
Yeah. So coming back to the affine transformations, and I agree that the total space of those transformations go beyond what we consider normal. But let's say for a machine system, it might make sense to stretch.
This is just a way of doing deformation. Is that correct?
So affine transformation is like what you see here. So it's any kind of linear transformation. And like one characteristic of those transformations is if you have two parallel lines and you transform it, it's still parallel.
Yeah.
And certain other things stay invariant, like for example, volumes. If you take the volume of, imagine those three volumetric shapes here, the volume of each of those under the transformation stays still the same.
Relative volumes.
Yeah, the
Oh, I was going to say, really?
The ratio. Yeah.
I mean, are you saying it's a linear transformation? Is that basically what it is?
Yeah, it's
It includes translation, scale, rotation, and the shear kind of things. It's all included in this.
all included. Yeah. So the translation you get here, the rotation you get with a very specific A matrix that has determinant of one other properties.
So maybe this is how we want to implement this. I'm not going to say no, right? But I don't think this is what's going on with it.
Yeah.
Okay, there's no way. This is what's going on. Then my example of the cup being rotated and not really being rotated is counter to this idea, right? There's no transformation between these two in my head. This is not. They're both valid views of the cup. I just see them what they are. I'm working on a theory that explains that. Where this would say no, there's a normal cup and then there's a rotated cup under some transformation. Mm-hmm. So that doesn't mean we don't want to implement it this way, because maybe we understand this better and we go that way. I just want to point out that I don't think it's capturing what the neurons are doing.
Yeah, I agree. So this is one way to sort of get a recognition. It's completely invariant in the rule. So it wouldn't recognize at all the pose.
It wouldn't? I thought
But
it would.
you could recover it.
Wait,
Once we cover the
I
object.
thought that is, the poses are not part of this transformation.
Oh, yeah, but it's if I, let's say,
It's
the ratio of the
3D
volumes.
rotation, and if this is 3D, I find it very, I find the
3D.
3D rotations, 3D scale, 3D movements, and
It
3D
would
share
work.
are all included.
I thought you said it wouldn't work.
What I mean is, it would work in the sense it would recognize it independent of the pose.
Okay.
So the pose is a kind of gets removed of the recognition system. It's
You can't extract the pose out for that?
yeah, once you recognize the object and
Once you
the
recognize it,
representation of the object, you
Yeah.
can recover. the
Yeah.
pose.
I used to think, okay, so that's good, it works then, right?
Yeah.
Okay. I used to think that, think about that in the brain too. I say to myself, well, I'm able to say what this is. It's a cup. It's my demented cup, but I'm also aware of its pose,
Yes.
right? So when I classify it, like what is it? I'm clearly not including the pose. The pose doesn't seem to be part of that, right?
Right.
And so I said, well, there must be some neurons that are representing the object just independent of its pose, and then there's some other neurons are representing the pose of the object. So there must be two parts of the neural population.
Exactly. Yeah, this was my point.
But the theory I'm working on now says that may not be true, right? That I used to think that, and it was always bothersome to me because it doesn't really kind of fit. But there's a lot of things that doesn't fit within the brain, and so I was thinking like, so this idea that you've got this sort of displacement sheet, which all of it is the object. And put the part of the sheet you're actually working in now is the state of the object, whether that's the pose or the state of the stapler or something like that. It's saying I've got this sheet that represents a sheet of displacements that represent the object. I'm only able to observe part of it right now, but I still classify the object. And the part I'm observing is the pose. It's not like I have two separate representations. It's like there'd be one representation for the two. So I think it's a very nice idea, but it's true, and I don't know, it's a very nice idea.
Right. I agree. It's a nice idea. I thought about it too. But my concern is that you get a kind of explosion of possibilities.
No, I don't think so. I don't think it is. I think it's actually quite efficient. So, I mean, at least the representation of the, I haven't worked all the angles out yet, but so far as I thought about it, if you take the cup and you just unwrap it, you're storing the same number of feature displacements as you would have otherwise. You're just storing them you're not storing them in a 3D structure, you're storing them in a 2D structure, and you're sort of playing it out, but it's the same number. It's like, I'm still just figuring out the displacement on a local point. I'm thinking of the displacements of these things. I'm not trying to figure out displacements between distant points. So I think it would work, but I haven't proven it. So I think I'm going to keep working on it. And I think if the argument here is we want to be working on these affine transformations, I think that's fine. We might run into problems. But so what? We might run into problems with anything. So I'm just pointing out that I'm not satisfied with it. I want to have. I think there's some fundamental things. There's so many weird things going on in how we recognize things in the world that I'm afraid it's one of these situations where I'm worried that we might really need to understand how neurons do this, because otherwise we'll just get it wrong and we'll get stuck in some local minimum sometimes.
Just a side note on what they showed. Those are what at least in my field, what were called barycentric coordinates, and they can actually work in higher dimensions as long as you decompose the object into simplices. So there's a two-dimensional form, there's a three-dimensional form. So they have the properties that you're talking about. They're invariant.
What was the term?
Was it barycentric? Is that what you said?
Barycentric, yeah. Weight heavy is kind of
How
what
do you
it's
spell
called.
it?
B-A-R-Y, I think.
Yes, B-A-R-Y, centric coordinates.
What does that mean?
It means it's weighted by the, if you think of it as a triangle where you have a point in the center and you form three triangles from that, it's the area of the triangle weights how much you would want to contribute to the coordinate. In other words, the distance from the face. So we use it in graphics for interpolation, for instance. Instead of thinking about interpolating, on a square, if you're trying to interpolate in a triangle, barycentric coordinates is what you use to kind of weight the contribution from, say, the color of the vertices to the interior color. So it's something that works transformationally, when you pass it through coordinate systems, and still produces good results. So what they were showing there was, rather than breaking a triangle into 3 triangles centered at the point, they're breaking a tetrahedron into 4 tetrahedrons. So that's it's a 4 tuple rather than a 3 tuple, but that still can go up to higher dimensions. So it is a way of making something that's invariant to those kinds of affine transformations in higher dimensions.
Barycentric coordinates. Yeah. Thanks for the link reference, Kevin.
Yeah.
All right. Yeah. Thanks, everyone. Yeah. Thanks, Jeff, for the feedback. So let's move on to the next presentation. Luiz.
Okay, so last week we talked about the touch sensor, which was this version. That yeah. So we give just kind of sensitivity, and we have like a simulator of it. So, but then Jeff pointed out that it's not really how it works, because we move a finger to the side, so we hit something, or we have multiple sensations in different sides of your finger. Mm-hmm. So the same group, the same researcher went together with the university, created this version.
That was quick.
So this is basically the same technology. So the one that we talked yesterday is in the left there.
The left there, I see.
Is the left one. So it basically has a camera at the bottom and the gel on the top. This one.
What do the LEDs do in this case?
They put light.
Oh, they put light.
Because there is a coating on the top of the gel that doesn't let outside light come in. So they only see the deformations in the gel.
They have different color LEDs to.
They have different colors.
To sort of know where you are on the sheet.
Something like that.
And they probably alternate them or, yeah, okay. It's a little bit like how you might make a touch. The way we used to do, figure out where your finger or your pen was touching the screen. You had to have different sources and you alternate them. Okay.
So on the left side, that's what they presented last week. And they use like, they use this gel, these LEDs, and they have a little casing, and they have like this web camera at the bottom. On the right side is the new version, which uses 5 cameras, and they are endoscope cameras because they need a lower focal point, a smaller focal point, and there is no casing. It's just they put the gel on top of the cameras. So the distance is basically the size of the same, the size of the pump.
So there's no air inside, it's completely.
There's no air. It's completely.
Oh, it's completely gel.
It's completely gel. So the thing on the right is a physical sensor, and they wrap that in a gel.
Wow.
So the whole thing is gel, 360 and 270 on the top.
So this, if I was thinking, this is, well, I keep going. This is pretty cool.
So
That's amazing.
so that's and then in the 5 cameras, say there's some blind spots, as you can see on the top right. So this is the field of view of the cameras, all the 5 cameras. So the B is the top view.
So I mean, like, this is one field of view, this is another field.
Yes.
So right here is the blind spot.
Yeah, and you can see in the diagram on the middle.
Yeah.
Yeah.
Diagram in the middle says top view and the side view.
They're amazingly small, this camera.
Those are endoscope cameras. So that's medical grade.
So they can use this for, some interior exam instead of the doctor figures.
Yeah, they go up the nose or something.
They stick a finger up your nose.
Other places that we don't want to talk about.
Let's go the nose.
The robot Well, now do your exam.
But those are the cameras they use those cameras because they have because they put the gel, there's no room
Yeah, yeah.
between the camera and the gel. So they need a much smaller focal point. I think it's 5 millimeters.
Why do they do this? Did
The
they-
same reason you mentioned.
Okay, so they came to the same conclusion?
They say the same conclusion that, on the going sideways, look at you cannot see
Yeah,
what's going on once you move the finger. So they came to the same conclusion. So in this sense, like you see the top one is just the top
yeah,
and the bottom is like as they moving the finger.
yeah.
And then you get into different camera.
They got different cameras. Right now they're seeing the side camera and the top camera. Those are the different.
Well, you could make it, you could basically, so within the camera's field of view, well, even then they have resolution within that, right? You
Correct.
can tell who's on the left or the right.
Yeah, they have one.
So even the old one is more than just a single, I mean, if you think about it like a sensory patch from a patch of skin, as I mentioned before, it's not resolution like this. You can't
Right.
feel the entire,
Yeah.
to feel something like that, you have to feel multiple parts of your skin. And so this is actually, this is sort of an array of sensors. We could break it up into 5, you could break it up into 25. You could take each of those and break it up into further pieces.
Right.
That should give you a lot of flexibility here.
Yeah, it's just a different configuration of the same
Yeah,
technology, basically.
yeah.
So you can do that.
Do they have a simulator for this?
It is. And they have the same simulator that we had before that I presented. They have a version. So you see like the marble goes to the sides and the bottom
Yeah,
camera.
yeah.
And you go to the top, is on the top camera.
They didn't really simulate it like physically, right? It's just,
No, they have a mesh for the gel and they have like they apply the noise from the
they
camera.
have different camera fields.
Yeah.
Or is it all one continuous thing now?
No, those are 5 different cameras.
50.
Right there. Those are 5 different cameras and they apply the same noise they get from the real sensor. So they compute the level of noise there was and apply that.
Wow.
So I have I can show in the paper where they give the real versus simulator ones. But like,
If you were to run this simulator, would it be like super slow and we would say, oh my God, we can't do this?
yeah, that's what I'm reading right now. So it is not as fast as the other one because there is a physics component in it.
Yeah.
Because the pressure of the marble on the gel is simulated by physics.
Wouldn't they have that in the old one?
The other one we didn't have physics.
But they still had the ball on the gel. But,
Oh yeah, the old one, yeah. Those are all that's the same simulator as the old one. It is the same exact simulator, just they just implemented this configuration into that simulator.
This is more like you've got 5 of them instead of 1.
Correct.
And maybe there's the physics is a little bit more difficult because you have to figure the angle of
Right.
the
So
thing.
I'm trying to figure out what is now the frames per second I can get out of this.
Do they provide the source code for this?
Yes, it's all open source.
So you could make a simplified version of this that didn't correspond to the physical sensor.
Correct.
So like, what if we said, hey, for our purposes right now, a lower resolution system would be okay
Right. Because right now the resolution they have is 400 by 400
for each camera.
for each camera.
That's a lot.
Yeah.
It's a lot. That's superhuman.
Yeah, I mean, there's nothing like this.
Yeah. So that's what they have right now.
Well, this is a bit more like this game. I mean, I don't know. I don't,
Yeah, we could do it.
the data is probably out there about, if I think about my fingertip, how many different sort of cortical columns are representing my fingertip? I don't know that number.
Yeah, with this one, with one touch, you could read a paragraph.
So I mean, this is not like this is superhuman, but it's really more like, the equivalent for a human might be, I don't know, 50 columns of that are fairly low resolution type of, that each one's not capturing an image.
Right.
Like when someone reads Braille, this would be interesting to know. There is there's a very simple test you do. On the skin, you poke the skin with two pins, and then at some point when they get closer together, the humans can't fill them apart. At some point they do fill them apart. So that in some sense is probably sort of the scale of your cortical column, right? In some sense, maybe a good guess. And so I think on the tip of your finger, it's pretty close, right? On the back of your finger, it's pretty wide apart. If you do it on the back of your back, it's surprising. You have two pokes like an instrument, 2 inches apart, you can't tell the difference. So I'm just saying, I'm just trying to figure out what would be equivalent for a human figure here. But that's just pretty cool.
Yeah, but I think we have flexibility too.
My point is, if it became slow, if we were using this and it became slow, we might have options of saying, we don't need all this resolution.
Correct. And it's open source the same way as the other one before.
Because this seems like it would be higher resolution than a human finger, right? If you got 400 by 400,
Yeah, that's why.
in a little patch of your,
What's the camera they got?
okay, that is far greater resolution than you're gonna get on a human finger, right? And we might want to be just like touching, like basic deformations as opposed to like reading the micro cracks in my ceramics here right now. Oh, yes.
Yeah, so you guys, that's the, look at that, the screwdriver there.
Yeah, I know. So it's like a camera. Yeah. Whole thing. Is this the same team that did that?
It is the same researcher, but like this is a university, it's not Facebook. This is Berkeley.
Yeah. So Berkeley, same team, they built this.
Not the same thing, like
It's a collaboration.
collaboration between the main author and the first one and Berkeley. But the main author is from Facebook.
Oh, I see. I didn't understand that. I forgot.
The main author is the guy who built the physical system.
They built the first one and the simulator. This is all Facebook. But like Berkeley took that and built this sensor with their collaboration.
Oh, I see. So Facebook did the first one.
Yeah.
And then Berkeley did the second,
Correct.
but collaborating with the guy who did the first one.
Correct.
Okay. Interesting. What are they doing with it?
That's a good question.
Metaverse.
Maybe.
Oh, so tomorrow there is a Facebook talk at 9 about how they're using AI in the metaverse.
Yeah.
I actually want to attend to see what they're doing with all that.
I mean, how would you use it in some sort of virtual reality? Because it's like you'd have to have a remote hand that's remotely sensing something physical, right? Or I guess it could be just a simulator. It's remotely sensing something through the simulator. But would it be like my hand? Is that the idea that my hand would be moving and this thing would be in some remote world?
Well, if there was a representation of my hand in the metaverse and I touch something, it would need to know the exact sensation to be able to then transmit it back to me.
But then you would try to activate your hand.
You need something corresponding to this to activate my hand.
Okay, so then all this high resolution really wouldn't be advantageous in that sense because your finger can't tell. I don't have this resolution.
Oh, there is
It also has applications in telepresence.
Yeah,
Now you can pass the sensor back.
isn't that the same? How's that different than virtual reality?
Well, the difference is you actually got a remote effector, like a robot sitting there that's got a hand and it
Oh, I
reaches
see. The
out and
metaverse
touches
is
something,
virtual
feeds
and
it
this
back
is
to you.
It's
Yeah,
a real.
That's what I started thinking like. I was thinking like, oh, your hand, there's a physical robotic hand sensation, you're sensing it, but then I said, well, the metaverse wouldn't be like that. Yeah. So yeah, I can see that. Like you're trying to fix the space telescope from Earth and then you've got your hands up there manipulating the space telescope or something like that.
Or anything remotely, if you're a surgeon or something like that. I mean,
Yeah,
it's
Yeah, I got it. Although, again, there's sort of a mismatch between the capabilities of this and what your finger would be able to do.
Right.
Well,
It's communicated to.
it's-
I mean, this is kind of cool because, I mean, in some sense, if you had a robot, if you were building a physical robot with a brain, then that robot would have, it could have superhuman tactile senses, right?
Yeah, I think that would be the exciting. Maybe we could do some manipulations, otherwise we're.
I've said multiple times, I thought another cool, superhuman capability is to be able to sense at a distance using your fingers. So as you approach something, before you actually touch it, you would be able to start sensing it.
Senses.
Yeah, but it'd be more like little cameras of vision on each finger, and you could, right? In some sense, you could start seeing it, feeling it before you actually touched it, and so you'd be able to see an object just by doing like you'd be able to feel the object just by like doing this. You'd already be able to perceive it or learn it, just in the sense like we move our eyes around, just like moving 5 little eyes around, but then you could also grab it and do it, right? So you could combine the sort of the sensing at a distance with sensing on the surface with robotic manipulation. So you have like this super hand.
It's a little surprising. There's like no organism I can think of that has anything remotely like that. Like evolution seemingly just didn't cook that recipe.
It's an interesting question.
Well, maybe
Well-
like echolocation or sonar.
Yeah, a little bit like sonar. So
Sometimes the
has to be-
whiskers are a little bit like that. They do touch it, but it sort of
They
gives you
are.
a feel before you actually, but it's not exactly the same.
I think there are some crabs or maybe something that have eyes that are actually kind of like extended on things.
yeah, but the question is, combining it with the actual physical manipulation is the interesting thing, right?
Right.
It's not just like a bunch of eyes on stalks. It's like, but I can also grab this thing and, is combining sense at a distance with sense on the surface with physical manipulation, which is kind of unique. I'm answering your question.
You also have to see what the limits of human beings, especially trained ones. I mean, the claim, I remember seeing, some pride that this one Japanese machinist claiming that he could basically sense things down to, 1/10 of a mil. So surface discontinuities still require a huge amount of precision, and somehow we're able to do that.
I'm sorry, that was using touch or what was it?
That was touch.
Yeah.
I mean,
Yeah,
you can feel, a human hair if it's on a surface. I mean, that's the level that we have.
Yeah. And people who, we all have this ability in some sense, but people who are blind develop it much better, is they can feel the presence of walls as they walk around. And I forget what the research says about this, how they do it, whether it's through sound or through it's like radiant temperature. I'm not sure.
I can frankly just tell you, I can sense walls around me using my ears.
Just the sound of it. Yeah.
It's because of sound engineering.
Okay.
Now I just walk into a room and I'm like,
Yeah.
oh wow, the sound is so different. in
Yeah,
this room.
yeah. Anyhow, that's an interesting observation. Are there any animals that have sort of a manipulative grasp that also has sensing at a distance combined with hares, are a good example, that can up to a little bit.
I think evolution would select against it
Why?
because a predator or you could lose it from just dangerous circumstances.
But why would it be worse than having, it seems like an extra capability that can only be advantageous. How would it get worse?
Because you don't want to experiment with a part of yourself.
It's just like,
Maybe
all I'm giving you the
more
ability
resource
to,
intensive or something. So you're putting this like,
maybe, but all I'm saying is that you're getting an additional capability. You don't have to use it. So it's not like forced you to do something dangerous. I mean, imagine if I was just able to, really sense this object before I touch it. I don't see how that would make it more dangerous for me. It just seems like it'd be better. I mean, almost like, oh, don't touch that because I now know from a distance it's going to be, I don't know, something bad.
I mean, actually, I guess the tongue is maybe the closest because you have receptors on your tongue. They're not
Yeah.
like cameras, but they're different types of receptors.
Yeah. Anyway, but something has to be on the surface, right? Anyway, okay, very interesting. Yeah, interesting. I like this. It's good. I'm glad this happened because.
You brought up the same date, you also brought the same issue.
Did you read it, their description of why they did this? Was there anything additional that we didn't think about that's in there?
They say like, that's sometimes the task, exactly what we said, like sometimes they don't have the actual sensation. They have to move. Sometimes the object goes around, like.
Okay, so yeah, so yeah, I
The
didn't
object-
know if there's any additional stuff in it. Yeah, like this gets back to we were talking a while back with Vivian about like, how do you, when you move your finger along the edge of an object, you get to the edge, how do you know that? Well, one of the reasons you don't just go off the end because you can actually sense, there's some senses that are sort of kicking in saying that no, it curves around.
I think the experiment, the experiments that move. They didn't have the same budget as Facebook, so they have a 3D printer instead of a robot to do the experiments.
They have a 3D what?
They use a 3D printing instead of a robot to do the experiments.
Oh, they're actually, you're saying they're moving this finger on a 3D printer.
Yeah. So they have a CNC machine.
I see. Yeah.
And they move the finger instead of a.
Okay, that makes sense. Yeah. It's cheaper than a robot.
Yeah.
Well, they're very creative for sure.
So, you know, lower budget than our Facebook
Grad
budget.
students.
All right, well, this is encouraging.
Oh, yeah.
It's
Thanks.
very spooky seeing those little lights glowing in there.
Well, it's all LEDs
I
around.
know, but it's definitely gonna give you the heebie-jeebies if you saw someone's fingers glowing like that.
And, you know, had a little bubble they have in the child. Because they didn't
Yeah,
got,
it's like, I'm coming for you. Ah!
you can also see the little bubbles, they didn't get a perfect seal there.
Oh, gosh.
Those air bubbles.
Interesting. Okay, that's interesting. Very
Doesn't
good.
that distort the vision of the bubbles? Isn't it, are the bubbles visible?
No, a little bit, it's in a little bit.
Those like the bright spots. right?
Yeah,
You know, if this was learning from the beginning, it wouldn't matter.
Yeah.
Just like you have you have problems with your retina, you know, the blood
Yeah, you
vessels
see those
coursing to
little
your retina,
bubbles.
you don't notice that.
see the bubbles in here, some, the little white dots
You know,
there.
people's skin is not the same. Ah, very cool.
Cool. Yeah. Yes. All right, Ben.
Cool. We don't have a ton of time, so I think I'll just try and present the shorter of my presentations.
Yeah.
And okay, basically there are just a couple small things in our current diagrams for the Monty architecture that are a little ambiguous. So I wanted to raise those and try and get some answers, or at least start thinking about them. And also update you with some changes we made to the code and try and make sure that those things that are ambiguous and the decisions we made in the code are going to be compatible with the overall picture. So here's the diagram.
You know, the people to the right.
Yeah.
Or just minimize it. Oh, look at that. Just very blue.
So yeah, this is from our documents.
On the screen share, it still shows the first slide.
So it's not showing that, but that's complicated.
Okay.
Can you just, on the right screen here, just click on the second image.
We'll do this manually. How about this with you?
Nice. Yeah, that's perfect.
I came up with a solution impossible.
Like, I don't understand anything.
Just do both of these.
So when you move the mouse now, I have to keep in mind, they don't see your mouse.
Yeah.
Okay, so just verbally describe it.
Let's just do it all on this.
Yeah.
So you won't see the animations.
We
but,
see his mouse.
The first question was, where do sensor modules live? Like, where do they begin and end? So is it kind of like it's a sensor module is like the sensor that's in the body? Is it something in the brain that processes the sensory input? Or is it sort of both? Like it would be like the retina as well as some like early processing.
I mean, you're talking about biology or in Monty?
Monty. I don't know where a sensor module actually begins and ends.
And in Monty right now, everything's code, right? I mean, we don't have any physical sensors yet, so.
I mean, Monty, like conceptually speaking.
I can take a stab at this, but I'm not sure how other people think about it. To me, the sensor includes, in the real world, it includes the physical sensor plus any amount of subcortical processing that has to occur to present in a format that's now can be fed to a learning module. So in the brain, it would be like, oh, well, I've got my eye, I have my retina, and that's that. In the ears, it goes from the cochlea to there's two subcortical structures, they're inferior colliculus and something else, and it gets processed and then it gets passed to the cortex.
That works. It's the sensor plus some subcortical process.
It would be anything that, it's not cortical processing, it's anything that's specific to the modality of the sensor that needs to be processed to get in a form that can be used by the learning model.
Perfect.
Oh, that was easy.
Works great for me. Okay, the next little thing I wanted to bring up is there's no attention on this diagram, and you know, there's just not enough dots and arrows here. So
Sorry.
I guess there's the motor command, which can move the.
well, so that's what I'm getting to is I think I've been tending to think about the motor command and the attention as intermixed, and I want to piece them apart because we talked at some point about the idea that you could give an attention signal in the form of a location in space to attend to.
Yeah,
So, but if that's the case, who decodes that into actual motor commands so that you move the sensor to attend that location?
I guess it would be the subcortical motor area.
yeah,
And then that leads to the final related question here.
yes, right, that would be, so that would be, again, very modality specific, right?
Yeah.
So the superior colliculus directs eye movements, and I think it works in coordinate systems like this. And so you would tell the superior colliculus, attend to this location, and it figures out how to move the muscles in your eyes and do all that weird stuff.
So on our Monty diagram,
That would be part of the sensor.
oh, so that's what I'm getting at. Is it, so
Well-
now the sensor has to be able to do that.
Yeah,
So here's why I disagree.
oh, okay.
So as a rock climber, I've had to become very acquainted with the anatomy of the hand. And what's surprising is there are no actual muscles in the fingers. They're remote controlled by tendons. So you can see that yourself by pushing down on your forearm.
Yeah,
The muscles in the forearm control the fingers. And also the muscles in the forearm don't move the forearm.
Yeah.
So when you think about motor commands, some action potentials are coming down from probably the motor cortex to nerves in the cervical region of your spine. And from there, they go out to nerves in your forearm.
yeah.
And then the muscles in the forearm contract, and that's going to move the finger, and that's going to change the position of the sensor on the tip of the finger.
So what's the problem?
But I think here you're using a different meaning of sensor than what Jeff used. So their sensor was
sensor
like,
module.
well, sensor was, all of the stuff you need, including the subcortical processing to deal with, in this case, somatosensory input.
But that's included.
And so the subcortical areas would also be the same ones that would translate stuff to motor commands.
So the one in the eye, does
Like,
include this superior colliculus part or not?
Yeah, the superior colliculus,
Is included in the sensor module of the eye.
well, that's according to this
Well,
definition, yeah.
these things can be distributed in the body, but just think of it logically. You have a signal says, move the sensor to attend to this location. And how it happens is that's a very specific thing relative to the body or the sensor. So the fact that the muscles are physically located in your arm makes no difference whatsoever. There's a signal that says, move your finger to this location, and somebody figures out how to do that. Right? That's not Monty's problem, that's the sensor problem.
Okay, well, I guess I'm slightly confused because
It still seems conceptually like the actuator is not part of the sensor. Like, I mean, the muscles can move multiple sensors at once together, and they are constrained. You can't move different patches on the same finger into different directions.
Right. But how that exactly how that happens is very dependent on the particular sensor and the particular morphology of the body and the particular instantiation that we create, right? And so that is sort of outside of Monty's concern, right? That becomes a very specific concern of the builder of a system to do that.
I just feel like it complicates things if we want to put this into the same bucket, sensors and actuators. I feel like it's conceptually much simpler to figure out if those are two distinct systems.
It's interesting. I thought it'd be simpler to make them one system. So you think it's simpler to make them two systems?
Yeah, I think traditionally, maybe the word is confusing. The sensor is typically thought of as an input
Yeah,
thing, not an output thing, but you're thinking of it like the modality.
I think of a sensor system.
Yeah, like all of somatosensory stuff is like, you do things that's specific to, touch and movement with fingers and stuff.
Yeah.
And visual modality would be the retina plus the motor commands that are, so maybe you think of it as a modality.
Maybe, or just
Or
more of a
just
complex system that does these
Right,
things.
right.
I mean, think about in our, if I want to direct my gaze someplace, it may not just be moving my eyes. I may have to turn my head. I may have to turn my body. But we just do this automatically. Like if I hear something back here and I need to look, my brain says, look at that thing. I go like this. I move my body and my neck and my, all this complex stuff that's happening. So to me, I just wanted to abstract that away and say someone took care of that. Now, I think, Vivian, you bring up a separate issue, whether actuators should, there's an advantage of having an actuator separate from the sensory system actuator. Is there an advantage to be able to say, I don't know. I thought it was kind of a wonderful idea to say, just unite them and say, okay, well, when I want to grab this object, maybe the right way to think about it is to move my sensors into these positions. Because then it unifies them. It makes it somehow seems more simpler in some sense. But you're
Yeah, I mean, they are already unified because we have a sensory motor system, so they already learn together anyways, and that's why it all works so well and it is so easy and effortless. But I still feel like conceptually those are two distinct modules, sensing and acting. They just learn together and learn to coordinate together.
But why do you feel that way? Why, to me, as what's wrong with the idea of saying let's consider them as one thing? Maybe that's not the way you've thought about it in the past, but what's the advantage of separating them out? Or
I just feel like it complicates things a lot because motor actions, they can have a lot of different goals. Like you can move your hand in order to sense stuff. You can move your hand in order to do stuff in the world. You can move your hand in order to move an object into your visual field and in order to see it. You can do the same action for a lot of different reasons. And same with sensing. You can sense a lot of different sensations while performing the same action.
Yeah, I guess I was hoping that would actually be, we could unify all those things into one thing. It's, when I thought about manipulating things with your hand, for example, or your arm, it's hard to separate the fact that you're sensing while you're moving the object, or it's hard to separate out, oh, I'm touching an icon on my screen from the fact that I feel it, right? I feel it and I see it, and it's actually doing something at the same time. So to me, it was sort of like separating out of the sensation from the actual action seemed like that doesn't seem what we do. I can't separate them out. My body is, every time I do something physically, I have to sense it. So I thought that was a very simplifying concept. But maybe we don't have to resolve this right now. You can have them as separate, but the point is, if I want to attend to something, let's say physically by moving my finger, I have to give it a location, and somebody's going to have to figure out how to move the finger, right? And if you want to say, oh, now I want to grab something by moving my finger to that location, well, you want to call it a separate operation, that's fine. But it seems like, I guess in some sense, it's outside of the sort of the learning module. It's more into this subcortical stuff, and how we do that could be done differently. Does that make sense?
Yeah, definitely. I mean, I'm not trying to have action independent of sensation or anything. I'm totally on board with them being a completely combined system, and it's probably just a very conceptual distinction.
Well, but in some sense, it becomes, as long as that distinction is kept outside of Monty itself, that's I guess the question is. In the brain, the parts of the brain that control the movement of your limbs are the same parts that get input from your limbs. So how that's implemented outside subcortically, I don't really care. If it starts affecting how we think about the learning algorithms, then it makes a bigger difference. So I guess I'm saying I'm indifferent to how we do it outside of to the left of the learning models. But if you think it actually changes the way the learning models.
We're approaching that point where we may have to start thinking about it, because this is what we have in software right now.
Right there, yeah.
The actions that you can specify in software are like, move this thing, like this part of the body 30 degrees left. I don't get to say, the software is not going to take care of, give me this location in space. It's not just going to do the motion planning to like, handle all of that.
Oh, we could do that.
I'll be outside mounted.
Yeah, as long as it's not in the,
Okay.
because how you do that depends on what your physical manifestation of this thing is, right? I mean, if it was a body like with tendons is one thing, if it's a robot with 6 joints that have, stepper
Yeah,
motors, it's something else.
Could do invert kinematics and apply it and do that. That's one way to do it. There'll be no learning module. There'll be just a technique.
Yeah, the module would just say, put your fingertip in this location and body coordinates,
Yeah,
and then this other system would figure out, independent of how many joints you have
Yeah.
or what system you have to get it there.
So that's like a solved problem. We can just like.
That's-
Oh, yeah, yeah,
Yeah,
the
that's
robotics,
robotics.
that's totally solved, yeah.
Yeah. That's invert kinematics problem. There's no learning there. There's just location go there.
Okay.
So again, I think this is a general rule. We want to think of things like that are sensor module. I mean, things that, the learning modules have to be as close to generic as possible. We may not be able to get there, but we want to be as close to generic as possible. And when it comes to sensor modules and the ability to move the sensors and to manipulate things, that's all, that can be very specific to the implementation. There could be multiple ways of implementing it, multiple different ways of doing it based on what the system looks like. Again, I mentioned that you can have a camera in the corner of your room that doesn't physically move at all, but you can still give it directions to say, attend to this location, and it can do that without physically moving anything. Or you can have another camera that turns and looks. Or you can have another camera that has a little robot and runs over there and looks. I mean, it doesn't really matter how you do that. Okay.
But I can listen to the rest of it.
Thank you. So,
So are you okay with that answer? Or is it?
yeah, I mean, I think I first off, I learned a couple things, and I think I'm okay with the answer. I just want to make the diagram clear. So is there?
Well, this diagram doesn't show anything besides sensor patches. It just shows them pointing directly to the learning modules. So it doesn't show any ways of moving the sensors, or like it just doesn't show the entire
this doesn't
sensor
actually
modality
even-
system, right?
Yeah, actually, I didn't notice that till now. I grabbed this and I thought it was a different image.
Oh, I don't know what, I mean, this gets to the point we're making earlier, that a sensor modality has complexities of what it does, and that's not reflected in this particular picture. This just sounds like we're just taking something from an image patch and putting it into the learning model.
So, okay, so in the way you're thinking about it, sensor module includes like it's the sensor, it's subcortical modality specific processing, but it also includes access to like a motor system of some kind.
Well, it has to, yeah. Think of it this way: the sensor has to tell you where in space it's sensing, right? That's one of the things we've defined. It's not just like what's on the tip of your finger. It's where's your finger relative to the body. That has to be provided, right? The eyes have to tell you where it is relative to the retina, right? What distance and so on. So we're already inputting location information. And then now from the sensor, that doesn't come from the retina itself. That comes from a whole bunch of other body parts that are somehow informing the cortex. Where's his eye pointing to right at the moment? And where's the finger relative to the body, which is a very complex calculation, but somebody's taking care of it. And then all we do now is, and the reverse goes. I can tell the sensor, I want you to attend to this location, and then it's going to do that. So it can either say, here's the thing, here's the location I'm attending to, or I can say, here's the location I want you to attend to. And so there has to be some sort of processing stuff that handles that.
So a cortical column, which is analogous to a learning module,
Doesn't do that.
each of those have their own motor output though. So what I'm trying to understand is the map of those motor outputs, sensor module motor outputs, and then like who gets the final say.
So we know in the cortex, there's these layer 5 cells that have a motor output. No one knows what they represent. I mean, they know their motor output because they project someplace that makes things move, but they don't know what the encoding that they represent is, right? And this is always, I don't know if anyone who's ever, maybe someone studied it, I'm not aware of it. So So like, if I have a bunch of cells active, what are they saying? Are they saying contract the muscle? It doesn't look like that because they don't project to muscles. They never project to a muscle. Nothing in the cortex projects to a muscle. So the cortex doesn't contract muscles. The cortex sends a signal to someone else who figures out what muscles to contract. And so what occurred to me recently, a possibility is that what these layer 5 cells are doing is they're passing a location information, not a muscular information. And because we know that the cortex is going to operate in location spaces, right? So it says, you know, and so that's a possibility. We don't know that. It's speculation, but we do know it's not sending out muscle information. So it's not saying these are the muscle sequences to do. It's not doing that.
But we think the subcortical areas are doing that.
Well, we know they are because someone's kind of, yes, we absolutely know that. So the pericolliculus has neurons that project to the muscles that move the ox, right? It's just, they do. So,
And is there any interplay between those? Like, are the outputs of those layer 5 neurons in cortex, those going to the superior?
yeah, well, yeah, they do exactly where they go. Yeah, that's the point. The point is you look at these layer 5 cells, they all project someplace that ultimately results in movement. Like even the ones that in your what we used to call motor cortex, which is really just sort of somatosensory cortex, they may project, if they're going to move your foot, they'll project down to some part of your spinal cord where there's a plexus of neurons, and that group of neurons then somehow sends a signal to move muscles. But those are coordinated activities, right? Those sets of neurons in your spinal cord are able to do complete reflex reactions, like how to move an arm away from something like that. So in theory, what you're sending to that stuff is, we don't know, but lately I've been thinking like, oh, well, the simplest thing to do is pass in, you know, location information and let it figure out what to do.
So I'm thinking maybe in this diagram, there are arrows, there are motor arrows coming out of learning modules back to sensor modules.
They're yes,
And then
they call them motor, but there might be location signals, right? That generate behaviors.
Yeah, good distinction.
Yeah.
So location arrows coming out of learning modules back to sensor modules, and then like actual motor arrows from sensor modules down to like whatever moves the actual body.
Yeah, and who knows how that's happened, right? We want to let that be up to the specific system design.
Okay, and then is there a single, right now we have this one subcortical motor area who's responsible for all moving parts. Do we have really one of those, or do we have independent sensor modules that each, you know, say, you know, move my left foot here, my right?
Well, I'm not, clearly I need to be able to move my independently move my sensors independently, right?
Well, you could say for each sensor you have a processing block that computes the appropriate motor commands.
Well, I mean, look, I can touch this with my left hand, I can touch this with my right hand.
Yeah, so just the question is just.
I'm consciously making that decision.
No, but there's a difference between look at the mug and touch the mug. As far as motor command.
Yeah, but I'm saying even touch the mug, there's differences between use my left hand and my right hand. So you can think on the spectrum, you have eyes and ears and different parts of your skin can all attend to that spot. So we're going to attend to that spot. Who does it actually, right? Who's actually going to do it? Is it my left hand or my right hand?
Or just looking at it.
Or just looking at it, or both? You know, so my point is there is some sort of cortical, it's not just there's a signal that's thrown out there and say, attend to this spot and go at it, somebody figures it out, because I can consciously decide to do it with my fingers or with I mean, I have some control over this. So obviously, in the columns in V1 projected as a pericolliculus, which control eye movements. They don't control your hand. So it's not like there's just one processing point that says everything goes through here.
Okay, yeah, so.
We could implement it that way, but maybe that would be effective, but it's certainly not the way, you know, I'm seeing in my back of my head saying, do we have to do it that way? You know, that's what I think the big brains do it. Maybe we can do it a different way, I don't know. On a simple robot, you might have a single subcortical section that figures all out for you.
Yeah, I would still pretty strongly be for not doing for separating it from the sensor patches, the motor movement, because I still feel like motor commands are not necessarily modality specific and not necessarily patch specific. You can say, I want to attend to this location, but then the motor area can figure out what to do to put a sensor to that location. And I feel like it should be separated from the individual sensor patches.
Okay, but just, do you think that you should separate out vision and touch, or should they all be part of the same system too?
The motor area could decide what would be the best way to sense.
Oh,
this
okay, well,
location.
neuroscience tells us that's not right. I mean, in neuroscience, every column that we know of has its own motor output. It goes some say subcortically. And so the visual regions project to the superciliculus, and the touch areas project to, I forget what it's called. Anyway, this division of labor is largely taken care of in the cortex in the brain.
Yeah, but also sensors are not the same as actuators in the body. Like
Well,
just
I
like
guess
Ben showed.
we already had that discussion today, and that's not, I don't think that's the way to think about it from a neuroscience point of view, but I'm okay if you want to think about it that way. But here's already a problem with that, right? If I can't specifically decide to use my left hand for something versus my right hand for something, if that is not part of the Monty system to make that decision, then you're going to be limiting yourself. It feels like.
No, you can still have this part of the Monty system. It would just not be part of the sensor patch. The learning module can still output information about this. It would just be processed by a motor area instead of a sensory area.
All outside of Monty.
Yeah.
All right, I guess that's a distinction we can let lie for now. Just bear in mind that it might lead to problems in the future. So, but for now, it's fine. I don't really care. I mean, it's not that I don't care. I don't see a problem with it for now. I mean,
if you find commonality, you can always fuse it later. So
yeah, it's just if you look at cortical columns, they have a motor output that they're sending something that represents something in their modality. So the tactile columns are sending information back to moving the fingers, and the eye columns are sending information back to moving the eyes. And if you want to say, okay, it goes through a separate channel for actuators, do you consider the eyes an actuator? They're moving them.
Yeah, the muscles of the eyes would be the actuators.
As long as you come up with a system that works, I guess that's fine. I mean, this again, I think anything that's still outside of Monty per se, that's modality specific, implementation specific, we can try lots of different things and see which works and what doesn't work. What the limitations.
I guess one reason to why I feel like separating is kind of important is because motor commands are not just for sensing. They are also for changing the state of the world. They are for communicating. You can do all kinds of things with motor commands that are outside of the sensing.
Right. But one could argue that when I move my hand, instead of doing sign language, I'm moving my hand. It's the same. I'm moving my sensors, even though I'm not sensing anything. It's the same things I'm moving. So whether you're moving it to touch something or whether you're moving to just put them in various positions, it's the same things. But I think I'm fine with this. It's all right. I guess I'm not going to object to that. It just, my prediction will come back later and decide that there's some problems with it, but I'm not certain about that.
a quick question: the proprioceptive nervous system, where you get feedback as to the actual position you actually achieved, where would you place that?
Good question.
I mean, I think we have sort of an answer to that in the current Monty architecture, because there's always like prediction happening. So you decide an action, you predict what's going to happen, and then you actually take the action, and then you update. So that's
I mean,
that's in the
you're updating something else other than the sensor you moved into position. There's something else that senses that, oh, I've achieved that goal. And then you have correction to that saying, oh, I really meant to move it a little bit further, but you're able to put your arm out at a particular angle, and you have feedback that in fact you've achieved that angle to some degree of fidelity, independent of whether you actually touch an object to give you the feedback that you actually got there. There's something else sensing whether the goal of whatever muscular action you sent actually was achieved. And in fact, it's all in dynamic tension too. I mean, so I'm just kind of curious.
Kevin, yeah, the way I've been trying to isolate these things. So one thing we just assume is that we know where our senses are, the pose of the sensors to the body, that's an assumption we're making we know. And the proprioceptive system, of course, plays a big role in that. But if we were just saying all we need to know is where the sensor is, its pose relative to the body, then we can just offload that to someone else to figure that out, right? It's not part of what's going on in the cortex or mind problem.
Okay.
That's it. But there's problems with that. Let me just say there's problems with that. If I want to move my fingers from one location to another, I have to know if my elbow is going to hit something along the way. And if I do, I have to then turn my hand a little different to get my finger over there. You know, there's a lot of weird stuff going on. So I'm not arguing that's sufficient. But at the moment, that would be a placeholder to say, let's just assume we know where our sensors are relative to the body. We have the ability to move. We have the ability to attend to a location via movement of the hands and the eyes. And therefore, we don't have to worry about the proprioceptive system per se. There has to be something equivalent to it that's providing this information. But I'm not sure I agree. I wouldn't say that that's the end all, because I see problems with that somehow our bodies know how to avoid all. If I'm moving my hand, it knows how to avoid all the obstacles I'm going to do to get there. You know what I'm saying? It's not just where my finger is, it's also where my elbow is and where my arm is and my body and all these other things.
No, I agree. And that's kind of gets further along the line of putting that motor system as a separate thing.
Yeah, that would be the easiest thing for us. Let someone else worry about it. Right.
Yeah.
Yeah.
Yeah, it depends on the specific implementation.
Right.
All right, yeah, it's already 12:18. Yeah, thanks everyone for attending. Some of the discussion, then we can continue.